Hello everyone. In this video, we are going to talk about exponential random variable and its probability distribution. The exponential random variable and its probability distribution is defined using this function. So this is the probability density function of exponential random variable. There's another formulation of this density function. Basically, we define another parameter called beta, which is 1 over lambda, and we can write the same density function in a different way. So if beta equal 1 over lambda, that means lambda equal 1 over beta. So that would imply we can write this same density function using beta in this way. So something you need to notice that x is a non-negative random variable. So some of results we learn about, like for example, expected value. When you calculate expected value of non-negative random variable, there is a simpler formula which we learn in module 6. So we can use those results when you're calculating expected value of exponential random variable. So in next three slide, I'm going to skip those three. Those three is going to introduce Poisson processes. So you can read about how to define counting process and what are the independent station increment, what's the definition of that, and then how do you define Poisson processes based on what you learn in these two slides. So I'm going to skip those three. Please read it, and then if you have question, let me know. So we are going to continue from slide number 19. So where we are going to connect, we are trying to understand the new parameter beta, which I defined a few minutes ago, and the lambda. So actually this lambda, when you define exponential random variable according to this function, this parameter is actually connected to the Poisson. So remember that for Poisson random variable, expected value of that random variable is lambda. So what is lambda then? The definition is basically average number of occurrence of event in given time interval. Depending on the time unit you are using, this is average number of occurrence. So when you redefine this using different kind of parameter, basically beta equal 1 over lambda, beta is going to be the interarrival time between two events. Because lambda is number of events, then beta become average time between two events. So it means interarrival time. So that's another way to say that is average waiting time between two events. So with this new parameter beta, I defined this earlier, you can rewrite the density function of exponential random variable in this format. So when you see a density function of exponential random variable, just be careful what kind of parameter they are using. Is it based on Poisson or is it based on beta? So you have to you need to be careful with that, because in next slide I'm going to talk about expected value variance. So depending on the parameter we are using, actually the value is going to be different. So here you can see the CDF, cumulative distribution function for exponential distribution. So it's going to be 1 minus e to the power negative lambda x. Now if you use beta, it's going to be 1 minus e to the power x over beta. This one is expected value of random variable x is 1 over lambda, which is going to be beta. Variance of x is 1 over lambda square, which is beta square, if you use that formulation. This is moment generated function. Actually, we haven't done anything. We haven't learned about that in this course. So if you know about moment generated function from another probability class, just keep this in mind. If not, you can skip it right now. One of nice property of exponential distribution is memoryless property. So random variable has a memoryless property if probability x more than a plus b given x more than a is same as probability x more than b. So the idea is knowing this extra information is not going to make any difference. It's more like you really didn't know anything about that. For example, let's say your x is waiting time, and its e is exponential distributed. So now let's say you waited 10 minutes, and what's the probability? You had to wait another 20 minutes. So you already waited 10 minutes, and what's the probability of you are waiting another 20 minutes? Given that you know that you already wait 10 minutes. So exponential random variable is memoryless. So that means basically it's more like you are waiting another, like the probability is same. And knowing this, that you already waited 10 minutes, is not going to change that. So that's why it's memoryless. So there's no memory about you already waited 10 minutes. So this, to prove this, like showing that exponential random variable is memoryless, is very easy. So what you need to do, you expand this expression. This is conditional probability formula. Which is going to be probability x more than a plus b, and x is more than a, divide by probability x more than a. So that numerator is going to be simplified. X is more than a plus b, divide by probability x more than a. Now, if you go back to the previous slide, from here we can see this is probability x less than or equal some little x. It's 1 minus e to the power negative lambda x. So from there, I can really deduct probability x more than x is just e to the power negative lambda x. So if I use that formula here, then this is going to be e to the power negative lambda a plus b divided by e to the power negative lambda a, which is going to be simplified to e to the power negative lambda b, which is basically probably x more than b. So we can see right away. So here we are using exponential random variable density functions, the survival function. So using that, you can really show that exponential random variable is actually memoryless random variable because it's satisfying this condition. So now we are ready to do a few questions. So the first one is tell you that insurance policy cover losses incurred by policyholder. Losses incurred follow an exponential distribution with mean 300. So that means basically if you use lambda formulation, it's lambda equal 1 over 300. If you use beta formulation, beta equal 300. So just be careful how you can define this. The PDF, I'm going to use lambda formulation. That's basically fxx equal lambda time e to the power negative lambda x, which is going to be 1 over 300 times e to the power negative x over 300. CDF, you can check previous slide, which gave you the CDF formula. So it's going to be 1 minus e to the power negative x over 300. Mean, we already know that it's 300. Variance is actually 1 over lambda square. So that's going to be, that's imply that sigma is 1 over lambda, or standard deviation is 1 over lambda, which is 300. Find the probability that loss exceed 100. So probability x more than 100, and we just did the survival function. This is going to be e to the power negative lambda, lambda times 100. So lambda is 1 over 300, so it's going to be the power negative 1/3. Calculate the 95th percentile. By the way, I missed the median. Let's calculate median. In order to calculate median, you set the CDF to 0.5 and you calculate that value. So this one is median, and it need to be 0.5. So we know that fxb, which is 1 minus e to the power negative x over lambda. In this case, actually x is b, and b over lambda equal 0.5. So that says that's going to tell us e to the power negative b over lambda is 0.5. And you take natural log both sides, so you will have negative b over lambda equal natural log 0.5. And then b is going to be negative lambda time natural log 0.5, or in other way, negative 1 over 300 log 0.5. That's the median. Now this one asking you to calculate 95th percentile. what you need to do, you just change this to 0.95 and you follow the same procedure. So after that, there's a question I would like you to try it. Calculate, there's a deductible of 100, calculate the 95th percentile for loss exceeding that deductible. So, so see whether you can do it. If not, please let me know. We can discuss the solution. So now we are ready to do few societal factories sample problem. So the first problem, take a minute and read it. So this one saying that time to failure of component in an electronic device has exponential distribution with median of 4 hours. Calculate the probability that the component will work without failing for at least 5 hours. So so we have a random variable x, which is time to failure, and it is exponential and with median of 4 hours. So let's try to calculate, like in exponential random variable, you need either lambda or beta, one of those parameters in order to define CDF or PDF. Since we know median, we can extract that. So right here, actually, we derive a formula for median. If you remember, in somewhere here, yeah. So I actually erased it. So let's derive it again. So I have fxb median equal 0.5. Actually, now the b is given, which is 4. Median equal 4. So that means fx4 equal 0.5. Now, let's use the parameter lambda. Then this is going to be 1 minus e to the power negative 4 times lambda equal 0.5. What I'm trying to do, I'm trying to find lambda. So that's give me e to the power negative 4 lambda equal 0.5. So now I take the natural log both sides. That tell me that lambda equal negative 1/4 time log 0.5. So once I know the lambda, then I can come back and then continue to the problem and then get the answer. The second part is actually calculate the probability that component will work without failing at least 5 hours. So time to failure need to be at least 5 hours. So X need to be more than 5. This is survival probability, and we know that it's negative lambda time X. In this case, X is 5. So e to the power negative 5 lambda, and lambda I just found. So substitute that and you can get the answer. So in this question, the question says that amount of claim that car insurance company pays for an exponential distribution. So X is, there's also deductible involved. By imposing deductibility, the insurance company reduces expected claim payment by 10%. Calculate the percentage reduction on the variance of the claim payment. So X is, let's say, payment amount before deductible. So basically, that's the loss. Loss loss amount and the payment amount is going to be really they are same. So this one is following exponential, and I'm going to use the parameter lambda. Let's use beta. Maybe that's because we have this. Yeah, let's use beta. So let's define another one, which is payment amount after deductible D. because once impose indeductibility, let's say payment amount is y. Now, if you don't remember, y is going to be what? Y is going to be 0 if x is less than d, and x minus d if x is more than or equal d. So basically this imply y is x minus d plus. Now, so let's calculate expected value of y. So I can see that expected value of y is going to be expected value of y given x is more than d time probability x more than d plus expected value of y given x is less than or equal d. Let me put this equal sign the other one. So that is probability x less than or equal d. So if x is more than if x is less than or equal d, then the claim amount is going to be 0. So this expected value is going to be 0 because y value is going to be 0, and when you take the x value, it's going to be 0. So what we really have is only the first part. So expected value of y given x more than d time probability x more than d. So the question is actually how y is going to behave. So the claim is y given x more than d is actually exponential. So our claim so mean is beta. So in here actually, if you use this parameter, this is same as mean. Okay. If you use the other parameter lambda, then the mean is going to be 1 over lambda. So that's why I like using this one, because I don't have to use the 1 over like fraction type formulation. Okay, so mean is lambda, then so how do we prove this? I can just take the Sevel function and see how it's behave. So probability y more than little y given x more than d is this is going to be a probability. Y is actually x minus d. Since x is more than d, y is going to be x minus d, which is positive actually. And that's going to be probability x more than y plus d given x is more than d. And for sure, since x is exponential, this is memoryless, and this is going to be basically you are going to get the answer e to the power negative lambda y. So that mean y behave the Sevel function of y is e to the power negative lambda y. That means the CDF of y is going to be 1 minus e to the power negative lambda y. So basically, if I want to calculate this quantity, that's going to be 1 minus e to the power negative lambda y. Then I have to assume that y is more than d. Okay, so let me make assumption. So then so that means basically expected value of y given x more than d is same as the wait a second. Here I had write the not lambda y. I had write the because I'm using parameter beta. So expected value of y given x more than d is going to be beta. So so I can apply that into here. So that would end up as beta time probability x more than d, which is e to the power. We know how to calculate this probability for exponential e to the power negative x d over beta. Okay, so once we have that, So I want to calculate the variance of new this random variable. So variance of y, let's calculate the variance of y. In order to calculate variance of y, I need the second moment. So this one is going to be, so let me write it more detailed way. I want the second moment, which is we write the same thing again, but this time it's for second moment. And this is 0. So we end up with this one. And we know that y is exponential. So the second moment of exponential random variable, if y is exponential with parameter beta, then the kth moment is going to be k factorial time beta. Actually, beta to the power k. Yeah, so it's going to be k factorial time beta to the power k. So because of that, this one is going to be, we know that now y is exponential with beta. So this one is going to be 2 factorial time beta square. Time probably x is more than d. That's going to be e to the power negative d over beta. So now the question says, if you go back and read the question, it says, by imposing deductible of D, insurance company reduced the expected claim payment by 10%. So what that mean? So that mean if you write the expected value of y, so let me write somewhere here. If you write expected value of y, that is going to be so expected value of y is basically if you look at here, s beta time e to the power negative d over beta. And then it also says expected value of y is 0.9 time expected value of x. Expected value of x is beta because x is exponential with beta random beta parameter. So this shows us that e to the power negative d over beta equal 0.9, or basically probability x more than d equal 0.9. The reason I am using that, I want to apply it in this instead of this notation, I want to apply 0.9. So now I have everything. So I'm going to calculate the variance. So variance of y equal expected value of y square minus expected value of y square. So this one we just found it's going to be 2 factorial beta square, and then this part is 0.9. We just found it here. Okay. By comparing expected value of y formula and then the what's given. So this is 0.9. Then in here it is going to be, if you look at it, it's beta time 0.9, but we have to square it. So if we take beta square, this is going to be 2 times 0.9 minus 0.9 square, which is going to be beta square 1.8 minus 0.9 square is 0.81. So that would give us 0.99 beta square. But beta square is actually variance of x. If you look at the x axis parameter beta, so that means Ex is beta, which we use right here. And then variance of x is actually beta square. So if I can write this as 0.99 times variance of x. So variance of y is 0.99 times variance of x, which means basically reduction of 1%. So variance of y equal 0.99 times variance of x, which is before we apply the deductible. So I guess it's a little bit longer than what we think, but this anyway we have to go through the explanation. And the explanation may be very short. You can read it and then see whether you can understand it too. Maybe that is easier than this to understand. Anyway, okay, so now we are ready to go to the next problem, SOA 1 point. Take a minute until I erase all of this and read the problem while I'm erasing it. So the problem says the number of hurricanes that will hit a certain house in the next 10 years is Poisson distributed with mean 4. And each hurricane result in a loss that is exponentially distributed with mean 1000. Losses are mutually independent and independent of the number of hurricanes. Calculate the variance of the total loss due to hurricanes hitting this house in next 10 years. For this particular problem, you need to know a law of total variance. So I'm going to write two laws, which is going to be very helpful over the time. Sometime we haven't done this in our class, but knowing that is very useful. So one is law of total expectation. This rule says if x is a random variable with expected value of Ex, and y is a random variable defined on same probability space, then expected value of x is same as expected value of a conditional expectation of x given y. So you have conditional expectation of x given y, and then you are taking the expected value of that. So that's the law of total expectation. The second law is law of total variance. This one says, assuming variance of y is finite, you still have all these condition, okay? Plus assume variance of y is finite, then variance of x is expected value given variance of x conditional on y plus variance of expected value of x conditional on y. So these two formulas are very useful when you are solving some certain kind of problems. So here you can see that the problem is saying that number of hurricanes that will hit certain house is Poisson. So basically number of hurricanes is random with Poisson with mean equal 4. Basically for Poisson parameter lambda equal 4. And then each hurricane result in loss. So If I write the number of hurricane as n, then n is Poisson. Then each hurricane result exponential loss that is exponentially distributed with mean 1000. So loss is exponentially each loss xi with mean. So I'm going to use beta formulation is 1000. Losses are mutually independent and independent of the number of hurricane. So calculate the variance of the total loss. So let's write the aggregate loss. So S is going to be x1 plus x2 plus xn. So here you can see n is random variable. So the aggregate loss is actually random. And each xi is also random. So I want to get the variance. So since you can see that index is random, I can really use the law of total variance. So I can write this as expected value, variance of S given n. So I'm going to condition on a number of hurricanes plus variance of expected value of S conditional on n. Now let's think about this. If n is fixed, that means n is known. So for example, this is what? Is more like variance of S given n equals some number, no? So if you know the n is fixed, then calculating variance of, so if n is fixed, then this becomes something look like this. X simple n. This one is known because n is fixed now. So you know the n. So now variance of S is going to be basically n time variance of xi because n is fixed. So you have n here and then variance of each xi. And by the way, here we have something very important. They are mutually independent and actually identical distributed. So because of that, so I can write this as n and the variance of each loss is exponentially distributed with mean 1000. So right now I'm going to use parameter which is beta. So variance of exponential distribution is beta square. So I can write beta square plus now variance, and then this time n is fixed. What's the expected value of? So expected value is going to be you have n time expected value of xi. So expected value of xi is beta. So I have n time beta because n time expected value of xi. You have n copies of xi. Each one is mutually independent and identically distributed. So you have expected value as beta. Okay, n time beta. So now this is constant. So you can take it out. So beta square, expected value of n. Then in here, when you take this, since this variance become beta square, variance of n. So n is exponentially distributed, n is Poisson distributed, number of hurricanes. So for Poisson, variance and mean and both are equal to 4, basically lambda. So this one become, I'm going to write the number, or if I want, I can write actual lambda. So that's going to be 2 times lambda time beta square. Now I can substitute value. Lambda is 4, beta is 100, 1000 square. So this is going to be 8 times 1000 square, and your answer is going to be C. So here we have another problem. So this problem is saying that models makes 3 driving errors, each independent resulting in an accident with probability of 0.25. Each accident result in a loss that is exponentially distributed with mean 0.8. Loss sum is independent of number of accidents. So basically we have the same setup. So we want to know the losses. So so if S is loss, this is going to be x1 plus x2 plus xn. So there are actually only 3 accidents. So n is random variable. but it can take 0, 1, 2, or 3. So you can have 3 accident, 2 accident, 1 accident, or 0 accident. But we don't know what it is, so it's a random variable. So now the question says calculate the variance of total unreimbursed. So insurance is going to reimburse 70%. So unreimbursed loss so unreimbursed, let's say S prime, that's going to be 0.3 times x1, 0.3 times x2, 0.3 times xn. So let's calculate we want the variance. So we take the variance of S prime. And I can apply the same formula, which we did, conditional variance formula or total variance formula. So this is going to be variance of expected value of S prime given fixed at n, then expected value of variance S prime fixed n. So actually we can do something easy. So this is basically S prime. If you look at this, it's 0.3 times S. So variance of S prime is going to be variance of 0.3 times S, which is going to be 0.3 the square time variance of S. So if I know variance of S, then all I have to do is just substitute here. So variance of S, let's calculate variance of S. For that, I can apply the rule. So this is going to be extra value of variance of S given n plus variance of expected value of S given n. So when n is fixed, let's say n is like some simple letter n, then what's the variance of all of this? So so we have then n of those, and then the variance of each loss is exponential distributed mean 0.8. So this is beta. So let me write the so variance is going to be then beta square. So each xi we have mean equal beta, variance equal beta square. So variance is beta square. Then the variance, and we fixed n, and then what's the expected value? That's going to be n of those, and the mean is beta, so it's going to be n beta. So now I can take the beta square as fixed outside. This one beta become beta square since we have the variance. So I need the expected value of n and variance of n. Now n is we have 3 errors, independent result, and accident with probability 0.25. So basically n is binomial with parameter 3 trials and the probability of 0.25. So then the expected value of n is np, 3 times 0.25, and variance of n is npq, 3 times 0.25 times 0.75. So remember we have np, this is n, this is p, and the other one is np 1 minus p variance. So I have here beta square 3 times 0.25, then here beta square 3 times 0.25 times 0.75. So I can so I know the beta is 0.8, so this is going to be 0.8 square. Then here I have 3 times 0.25 plus 3 times 0.25 times 0.75. So that's the variance of S, and I had used that in here, and then I can get the variance of S prime. So this is the last problem, and so this one says that an automobile insurance company issue a 1-year policy with deductible of 500. The probability is 0.8 that the insured automobile has no accident and 0 that the automobile has more than one accident. So if I draw a table, x is number of accident, probability x equal little x. So x can be 0, 1 or more than 1. So for 0 it's 0.8, more than 1 is 0. So since we need total probability to be 1, this should be 0.2. Okay, so now so let's write the so how the payment is going to be. So so the payout, so that's basically L. I'm going to use the notation L. It's going to be 0 if no accident, and then x minus d plus if accident. So let's calculate the CDF, probability less than or equal some little x. That's going to be probability L less than or equal x given accident time probability accident plus probability L less than or equal x given no accident and probability of no accident. So we need this to be 95th. So this one to be 95th. So 0.95. So I will write this one as it is, probability less than or equal x given accident. The probability of accident is actually 0.2. If there's no accident, loss is always going to be less than whatever the number, assuming x is non-negative. So this is always going to be 1 because it's always true. So 1 and then probably no accident is 0.8. So that tells us that 0.95 minus 0.8 divided by 0.2, which is going to be 0.75. That's equal probability loss less than or equal x given accident. So now let's try to expand this, because now we have actually two possibility, because x minus d plus, if you remember, that is basically 0 if x is less than or equal d, x minus d if x is more than d. So let's try to expand this. So I can write this as probability less than or equal x given x is less than d and accident. Anyway, we are in this conditional one, so I can write it as accident if you really want. And then the probability x less than d, then next one probability less than or equal x given x is more than d. We are still in the accident. Probability x more than d. So if x is less than d, loss is, this is random variable. Oh, let me write this. This is not, I have write L is less than d. Wait a second. Yeah, I may have defined here x is the real loss. Yeah. Don't get confused with this x. Okay? This is different x. Okay? X is real loss. And then here this is little x. Okay? These are little x. So this is real loss. If there's accident, then the real loss need to be more than d in order to make a payment. So this is little x. Then this is random variable x. And then this is random variable x. real loss. This is random variable, and this is random variable, and this is little x. Okay, so if so let me maybe expand this a little bit more. We know that L is x minus d, so I can substitute it here. I'm going to remove this, even though it's there, just to look it nice. We know that this is under accident, okay? So this would mean probably x less than or equal x plus d, given x is less than d, probably x less than d. So if x is less than d, x of course this is true. So that's going to be 1. So then we have that one only. And then this one is probably x is less than or equal x plus d, given x is more than d, probability x more than d. So that's 0.75. So I have 0.75. Probability x is more than d. We know that x is, if you read the problem, it says if there's accident, the loss before application of reactable is exponentially distributed with mean 3000. So this is going to be x is exponential with mean 3000. We are mean 3000, so this is going to be e to the power negative d over 3000. This one. Then I can expand this one. It's going to be a probability x in between d and x plus d. This is random variable. This is little x. Okay? Divide by probability x more than d times probability x more than d. So I have 0.75. By the way, this is probably x less than d, so it should be 1 minus. Okay? 1 minus. Remember the density function CDF of exponential distribution? Fx a is 1 minus e to the power negative. If we use beta formulation, it's going to be e to the power negative x over beta. Beta is mean basically. That's 3000. So I can calculate this. This is basically probability x less than or equal x plus d minus probability x less than or equal d. So that gives us 1 minus e to the power negative d over, 1 minus e to the power negative x plus d over 3000 minus 1 minus e to the power negative d over 3000. So now I can bring everything to other side, 0.75 plus e to the power negative d over 3000 minus 1. This side 1 to 1 cancel out, and I'm going to take e to the power negative d over 3000 as common factor. And that would result, actually I can write like this, and I can, so we know that d is, what's the deductible? Deductible is 500. So I can substitute d equal 500. Okay, so we are solving for x. Okay, that's what we are looking, because that's where we start. This is our 95th percentile. We want to know what is that number. Okay, so so right now it's more about using your calculator. So let's see what do you get, 0.75. So let me write one more line and I'm going to leave it to you to do try. So negative 1 over 6 minus 1 equal to negative 1 over 6. Actually, you can take 500 over, you can leave it as this. So this is cancelled out. It's going to be negative 0.25 negative e to the negative x plus 3000. So then you take the log, negative sign cancel out, log 0.25 equal x plus negative x plus 500. So that would, so I take that natural. So let's see what's this one. So the answer is x is 3658.88. We have an answer like that? 3658, yes. So that's the 95th percentile. So that's the end of this exponential random variable section.